Before 1948, if engineers wanted to control the flow of electrons to build electronic circuits, they relied almost entirely on vacuum tubes, often called valves. These devices required a physical vacuum. They worked by heating up a metal cathode to boil off electrons, and the evacuated space ensured those moving electrons didn't crash into air molecules and lose their energy along the way. But relying on tiny glass heaters had serious drawbacks. They were heavy, fragile, consumed massive amounts of power, and operated at dangerously high voltages just to push a signal through. The alternative emerged in the 1930s. Physicists realized that certain solid crystals could control charge carriers entirely within the solid itself, completely eliminating the need for fragile glass bulbs and intense external heat. In an isolated atom, electrons orbit at specific, distinct energy levels. But when millions of atoms pack closely together to form a solid crystal lattice, their outer orbits start to overlap. Because no two electrons inside this crystal experience the exact same pattern of surrounding electrical charges, their discrete energy levels smear out into continuous ranges, forming what we call energy bands. This diagram shows the foundation of that structure, the valence band. It's the baseline energy level where an atom's outer electrons normally reside. Right above it sits the conduction band, a higher energy state that is normally completely empty. For electricity to flow through a solid, an electron has to gain enough outside energy to break free from the valence band and jump up to the conduction band. The empty space between these two platforms is known as the energy band gap, measured in electron volts. The size of this specific gap is the single metric that determines exactly how a material handles electricity. This animated diagram shows the band structure for metals. In metallic elements, the conduction band is either partially filled to begin with, or it completely overlaps with the valence band. Because there is no gap to cross, a massive number of electrons are constantly available to move. This translates to incredibly low electrical resistance. Now look at the structure for insulators. The top platform has shifted far out of reach, creating a massive chasm greater than 3 electron volts. That gap is too wide for electrons to cross. Even if the material is heated, the thermal energy isn't enough to push them over the edge, meaning zero electrical conduction is possible. Carbon, in the form of a diamond crystal, is a perfect example. It has a towering band gap of 5.4 electron volts, keeping all its electrons strictly locked in place. But metals and insulators are entirely static. One always flows, the other always blocks. Neither gives you the precision required to process information. This brings us to semiconductors. Here, the diagram shows the upper platform lowering to a manageable distance, creating a small but finite gap of less than 3 electron volts. At absolute zero, they behave like insulators. The valence band is packed, the conduction band empty, and the material inert. At room temperature, heat provides enough energy for a few electrons to bridge the gap and enter the conduction band. The exact difficulty of that jump depends on the element. Silicon requires an energy bump of 1.1 electron volts, while germanium only requires 0.7. If you move down the periodic table to another group 4 element like tin, the gap drops to exactly 0, meaning it behaves as a pure metal. Because a semiconductor's gap is so small, we can use minor inputs like heat, light, or a tiny applied voltage to coax electrons across, turning the material from a blocker to a conductor on command. When an electron successfully vaults up into the conduction band, it leaves behind an empty space in the valence band below. This empty space is called a hole, acting as an effective positive charge. A neighboring electron can slip into it, leaving a new hole behind. As electrons shift forward, the hole appears to travel backward through the lattice. In a pure, intrinsic semiconductor, every jumping electron leaves exactly one hole. But by adding specific impurities, a process known as doping, engineers can intentionally create materials heavily stacked with an excess of either electrons or holes. Current in a semiconductor flows through 2 distinct pathways simultaneously: negative electrons moving in the conduction band and positive holes moving in the valence band. Mastering those 2 pathways allowed engineers to build complex solid-state switches like junction diodes and bipolar junction transistors. Long before the atomic physics was fully formalized, natural semiconductors like crystals of galena or lead sulfide were already being used as crude detectors for radio waves. Once the math caught up, the heavy, hot cathode ray tubes that powered early televisions were replaced by liquid crystal displays running entirely on solid-state physics. By figuring out how to manipulate a microscopic gap in atomic energy levels, we moved the mechanics of electroflow inside the solid itself, leaving the hot, fragile glass bulbs in the past.